Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 9P, word problems about curvature, power, and sag. So I'm assuming you've already viewed the video on Unit 9, and also you've seen the videos on lenses, on spherical mirrors, and on spherical refracting surfaces. Question 1. What is the power of a spherical concave mirror if the radius is 10 centimeters? So we have our optical axis and our concave mirror with vertex A and center C on the left. Radius is defined as the distance from A to C. Right to left is a negative number, so negative 10 centimeters, which equals negative 0.1 meters. The formula is the power is negative 2 over r. We plug in, and we get that the power is positive 20 diopters. The other way of thinking about it is that the focal length of a spherical mirror is half of the radius, and then you change the sign. You change the sign because the radius is measured in the opposite direction as the focal length. So for a concave mirror, the radius is negative and the focal length is positive. So the focal length equals 5 centimeters positive from F to A. That's 0.05 meters, and the power is 1 over F, which is again plus 20 diopters. Question 2, what is the refracting power of a concave spherical refracting surface of radius 20 centimeters, separating air, index 1, from glass, index 1.5? Optical axis, our concave spherical refracting surface with vertex A, center C on the left, index n equals 1 on the left, and n prime equals 1.5 on the right. Now the radius is equal to the distance from A to C. Right to left, it's a negative 20 centimeters, which equals negative 0.2 meters. The formula is power equals n prime minus n over r. We plug in, and we find that the power equals negative 2.5 diopters. Question 3, if the cornea of the eye is a single spherical refracting surface of radius 7.7 millimeters, separating air from aqueous humor, index equals 1.336, what is the refracting power in air and under water? Index equal 1.333. Round your answer to the nearest hundredth. So the cornea is the clear front surface of the eyeball. And what you want to do, as you should be doing with all questions, is to pause the video and see if you can come up with the answer yourself. If you come up with the wrong answer, you need to go and sit in the cornea. So here's our optical axis and our cornea with vertex A and center C on the right. We'll first solve for air, where n equals 1. N prime equals 1.336. The aqueous humor is the fluid behind the cornea. The radius is measured from A to C. It's a positive number, and 7.7 millimeters equals 0.0077 meters. Formula is power equals n prime minus n over r. We'll plug in our numbers, and we find that the power of the cornea is 43.64 diopters. Now, let's see what happens when we go underwater and open our eyes and try to look at something. Now, we have our n equals 1.333, or 4/3, and we plug into the same formula. And we find that the power now is less than 1 diopter. It's 0.78 diopters, which is why things can look blurry, when you open your eyes underwater. You will see more clearly if you wear goggles or a mask. Then there's air in front of your cornea again, and the cornea again is 43.64 diopters in power. Question 4, the reflecting power of a spherical mirror is plus 2 diopters. What is the form and radius of the mirror? So our mirror formula is power equals minus 2 over r. And we find that r equals negative 1. So that means that AC is a negative number. C is on the left, therefore it's a concave mirror of radius 1 meter. Question 5, what is the refracting power of a thin symmetric biconvex lens made of glass index 1.5 if the radius of curvature of one surface is 5 centimeters? So symmetric means that the radii of the two surfaces are equal with opposite signs. So I've drawn my biconvex lens with the vertices A1, A2, and C1 and C2 on the appropriate sides. And we are given that R1, which is A1C1, equals 5 centimeters. That's 0.05 meters. And therefore, the radius of the second surface, A2C2, is negative 5 centimeters, or negative 0.05 meters. Symmetric biconvex lens. So, at the first surface, n is 1, air, n prime is 1.5. We have the total power of this lens is the power of the first surface plus the power of the second surface. So the power of the first surface is n prime minus n over r1. The second surface, it's the second index minus the first index. So it's n minus n prime over r2. So we plug in our numbers. And we find that the power equals 0.5 over 0.05 plus 0.5 over 0.05, and it equals 20 diopters. Question 6, a thin convex meniscus lens is made of glass of index 1.5. The radius of the first surface is 10 centimeters, and it is in contact with water. The radius of the second surface is 25 centimeters, and it is in contact with air. What is the refracting power of the lens? Express your answer as a fraction. So we'll have fun with fractions here. Let's draw our optical axis, our meniscus lens. Oops, there we go. So we have A1 as the first surface's vertex, A2 the second surface's vertex, C1 and C2 are both on the right. We're given that N1 is water. Water's index is 4/3. N2, the index of the glass, is 3/2, which is 1.5, and N3 is air's index, which is 1. We have R1 is A1C1. We're given that's equal to 10 centimeters, a positive number from left to right, which equals 0.1 meters. R2 is A2C2, also a positive number. 25 centimeters equals 0.25 meters, which is 1/4. 1/10 equals 1 over 10. So our formula is total power is F1 plus F2, first surface's power plus the second surface's power. Each surface's power is derived from the difference in indices of refraction over the radius. So we plug in our fractions. Let's see, our first big fraction, the common denominator is 30. That's 3 over 30 on the bottom. You can barely see it, but there it is. Second fraction, common denominator is 4 over 1/4. And the first fraction becomes 5/3. The second fraction becomes not minus 1/4. Let's do that again. The second fraction becomes minus 2 over 1, or minus 2. There you go. So we got 3 as our common denominator, and we have our total power is negative 1/3 diopters. Question 7, the refractive power of a thin lens is +6 diopters. It is made of glass of index 1.5 and surrounded by air. If the radius of the first surface is 10 centimeters, what is the radius of the second surface? So we have N1 is 1, index of air, N2 is 1.5, the index of the glass is N3. Behind the lens, we have air again, the index is 1. We have R1 is +10 centimeters, which is 0.1 meters. We're looking for R2, total power is 6. So the total power is the powers of the first and second surfaces, which equal the difference in indices of refraction divided by the radius of curvature. We plug in what we know to solve for R2. And we find that R2 equals -0.5 meters or -50 centimeters. Question 8, a lens clock calibrated for index 1.523 is used to measure a thin biconvex lens made of glass of index 1.6. The readings on the dial give +4 for each surface. Find the power of the lens and round your answer to the nearest hundredth. So the formula we're using is the true power equals n-1 over 0.523 times the measured power. We're given that n equals 1.6. And we're given the measured power equals +4. So the true power equals 1.6 minus 1 over 0.523 times 4. And we work out the math. And we find that the true power equals 4.59 diopters. Now that's just for one surface. There are two surfaces, so we need to double it to find the true power of the entire lens. And we get plus 9.18 diopters. Question 9, a point source of light in air is located 20 centimeters above a plane refracting surface. Index equals 1.6. What is the curvature of the wavefront immediately after entering the glass? So this question is asking us to determine big U prime, the curvature of the wavefront that has been refracted. So I turned the diagram on its side, so we have light traveling from left to right. N equals 1, n prime equals 1.6. We're given the object distance, little u, equals am, going from right to left. It's a negative number and equals -0.2 meters. The power of this flat surface is 0. And the power formula equals n prime over u prime, little u prime, minus n over little u. Little u prime is the image distance. What we're going to do is find what that equals and then use that to calculate big U prime, the curvature of the wavefront. So we plug in what we know and we solve for U prime, which equals, drum roll, -0.32 meters. Big U prime equals n prime over U prime. That's 1.6 over -0.32. And we find the curvature of the wavefront equals -5 diopters. Question 10, a lens clock whose outer pegs are 10 millimeters from the center plunger is calibrated for glass of index 1.523 and is placed on a lens of that index and reads -10.6 diopters. What is the sag? Round your answer to the nearest millimeter. So if you recall the lens clock that I showed you in Unit 9, it's got a round dial and a flat edge with 3 pegs. The outer pegs are stationary. The inner one moves up and down. It's the plunger. So the distance from that middle peg to one of the outer pegs, that's the semi-diameter, h, which equals 10 millimeters. And we're given the power equals -10.6. So just to be clear, here's the lens. Here's our chord. Here's our semi-diameter h, and the sag is the distance from the chord to the back of the lens. So the power equals n prime minus n over r. Let's turn the lens on its side, having light travel from left to right. We have n equals 1, n prime equals 1.523. We're going to solve for the radius of curvature of the lens because we need that to plug into the sag formula. So we plug in what we know, and we find that R equals negative 0.49 meters, which equals negative 49 millimeters. Now, the sag formula assumes that the radius is always positive. It's an important thing to remember. So we're going to plug into our sag formula. Sag equals R minus the square root of R squared minus H squared. Positive 49 for our radius of curvature. And according to my calculator, S equals 49 minus the square root of 2301, which equals 49 minus 49.97. So it equals negative 0.97 millimeters, rounding up to negative 1 millimeter.